All right, guys. Well, this is the Impulse and Momentum Lab. So a few points I wanted to touch on before we get started with a few of the examples are some of this stuff. So you can see this guy, these guys here, and here are all on your equation sheet, and then I'm going to go over what's down below them here in just a second. So this right here, so Rx is just a reaction force. It can really be any force, so it can just be Fx times t. The reaction force is just a particular type of force. So this equation tells us that the reaction force times the time is equal to mass times the final velocity minus mass times the initial velocity. Well, that equation is great, but it's not exactly what we need to solve some of these problems. What we need to solve some of these problems is this guy right here. And so the reason that this is the same is because acceleration is essentially just the difference between a velocity at the end and a velocity at the beginning, hence the final minus the initial. Well, if we can just say that that's acceleration, we just take mass and distribute it to both, and we get mass times the acceleration. So that's how we get this formula. And you'll notice that a bunch of these have time in them. If some of these equations that we have, or some of the problems that we have, don't give us time as a component, that's fine. We'll just disregard time. So don't put a 0 there, don't do anything with it, just pretend it doesn't exist. And the reason that that works is because when you're taking time and multiplying it by the same thing, or multiplying the same number by different things on the same side, if you just disregard it, then the answer still becomes the correct proportion of if you had time. So if we don't have time, we'll just disregard it. Now, this one is dealing with the y component. So again, like we talked about in the last lab section, anytime that we're dealing with a vertical force or something in the y direction, we always need to compensate for mass and gravity. So that's why this equation is slightly different. So we have the reaction force of the y multiplied by the time plus mass times gravity times the time is equal to mass times the final y velocity minus mass times the initial y. And so we're going to do the same thing that we did here. And so now we just have ry times time plus mass gravity times time is equal to the mass times the acceleration of y. And so we'll need these two equations here, these guys, for problems 4 through 7. So those are pretty important to be able to understand. Now, for this stuff, this is for problems 1 and 2. So it's important to note the difference between an elastic and an inelastic collision. So I kind of drew out here what an elastic collision might look like. So we have one object coming from here, so object 1 and object 2, and they're coming at each other from different directions. And when they make contact with each other at this point here, what's elastic about them is, think about something that's elastic, like a rubber band, and it bounces off of something, so like a rubber band ball. Well, when they hit, they bounce off and then they go to their own separate paths, which is why we have object 1 here and object 2 here. So when we do the elastic collisions, there's going to be 2 equations for those, and you're going to get 2 answers, and you'll find that on your formula sheet as well. Now, for inelastic collisions, it's exactly the opposite. So when they collide with each other here, at some point, their motion is carried together in one final direction together. So for this, you'll only get one answer through one equation. So that's the main difference between the elastic and the inelastic collision stuff. And the last point that I want to touch on before we get started is another formula conversion. So here, J stands for impulse. So our impulse is equal to force times time, and you'll see on your sheet it's F triangle T. It's just Greek for delta, which means a change in time. Another way of just saying force times time. So we did the same thing by the property of distribution here. So since force times time, as we noted up here, so Rx was just another type of force. So this right here is force times time is equal to max. So when we distribute that property, we can tell then that impulse is going to be equal to max as well. And that's because it's the same thing as saying since force times time is equal to max, and that's what impulse is, that impulse can equal max as well. And so you'll need this formula as well. And so that's all the tools that you need to be able to complete this lab. All right, so now we can start with some practical examples. So I'm going to start with number 3, then move on to 4 and 9. And those all kind of touch on slightly different things that I discussed in the presentation just a second ago. So the first thing we're going to look at is momentum. So again, like we did in the other labs, go ahead and write down the information that you have. So we have our mass of the player, which is equal to 90 kilograms, and we have a velocity that's equal to 9.9 meters per second, and we need to compute the impulse, so the J, in order to get them to stop. So first off, we need to compute the momentum, and then we can compute the braking impulse. So the equation for momentum is pretty simple, and it's on your formula sheet. It's just this guy right here. So the P is momentum is equal to mass times velocity. So one thing that's pretty important also as you're going through all these formulas and all that for the tests, it's especially good to know what some of the different letters stand for. So P in this case is equal to momentum. So we just plug in the numbers that we've got here is equal to mass, which is 90, times velocity, which is 9.9. And then so we get our momentum is equal to 891. And the units for momentum are going to be kilograms times meters per second. So that's the first bit. Now we got to solve the next bit. So just like I was talking about earlier with Newton's third law, this applies perfectly here. So we have some football player that's going with this much momentum. Now we need to figure out what is going to stop them. So we know that it's going to be exactly opposite this number, but I'm going to show you how to get that. So we would take the impulse is equal to the mass times the final velocity minus mass times the initial velocity. So what we end up with is our impulse is equal to 90 times the final velocity, which is going to be 0 since it's going to the person that's stopped, minus the mass again, which is 90, times the initial velocity, which is 9.9. So when we do this, we end up with impulse is equal to 0 minus 891. Otherwise, impulse is equal to negative 891. And the unit for that is going to be Newton.seconds. So this is a good application of Newton's third law of some object, in this case it's a football player, going with this much momentum. How much does it take to get them to stop? Well, it's exactly the opposite, but this is the work that you need to know to get to do that. And it's very important if we were looking at, instead of getting him to stop, let's say how much would it need to get him to slow down till 4.3 meters per second. And then you would have a practical application for this problem. All right, so number 4 is one of the problems that we're going to use, like those ones I told you guys how to set up earlier. So again, we're going to go ahead and write down all the information that we have. So first we're given mass, which is 70 kilograms. And then we have a horizontal acceleration of negative 9.6 meters per second squared. And a vertical acceleration, so AY of 14.2 meters per second squared. And these say draw a free body diagram and mass acceleration diagram. You guys don't have to worry about that, but do know what they look like because you will have some of those on the test and you'll need to be able to identify what they are and kind of decipher exactly what they mean. So what we need to do here is we are looking for the Rx and the Ry. So this is a perfect application of the problems that we looked at earlier. So now we know that the Rx is equal to mass times the acceleration of x, which is very simple because we already have all that stuff right here. So Rx is equal to 70 times Ax, which is negative 9.6. So when we do the math here, we get Rx is equal to negative 672 newtons. So we're going to do the same thing for Ry now, but since we're dealing with any type of vertical force, we need to compensate for mass and gravity as well. So we'll do Ry plus mg is equal to may. And so we already have all these components as well. So Ry plus mass, which we know to be 70 times gravity, which is negative 9.8, is equal to mass again, which is 70 times the acceleration of y, which is 14.2. So when we do the math here, we get Ry minus 686 is equal to 994. So now we need to get Ry by itself. So what we do is we add 686 to each side. And so now we're going to get Ry is equal to 1680. And that again is in newtons. And so that's that one, and you'll do the same for the next few problems. I'm going to go ahead and look at number 8 instead of number 9 because number 9 requires an answer from number 8. So same thing, write down all the information that we're given. Mass is equal to 78 kilograms. The horizontal velocity, Vxi, is equal to 5.6 meters per second. And the Rx is equal to negative 108 newtons. And our time is 0.2 seconds. So what we need to do is we need to find the Vxf, and we need to find the braking impulse. So now we already have all of the equations and stuff that we need. It's just a matter of picking the right one. So we're going to go back, and this time we're going to use the full version where we have time as well. So we have Rx times time is equal to the mass times the final velocity minus the mass times the initial velocity. So now we just start plugging in numbers. We get negative 108 for Rx. Time is 0.2 is equal to our mass, which is 78, times our Vxf, which we don't yet know. So we're going to have to isolate that later, times our mass again, which is 78, times our initial velocity, which is 5.6. So now the first thing that we can do is go ahead and multiply this side right here, and we get negative 21.6. And I'm going to go ahead and put a square around this for now, and I'll show you why I did that in just a second. Is equal to 78 times Vxf minus 436.8. So now what we need to do is go ahead and add minus 436 to over on this side. And so when we do that, we get 415.2 is equal to 78 times Vxf. And then in order to do this, just divide both sides out by 78. And then we get our Vxf, which is equal to 5.32 meters per second. Now, that solves the initial problem of our velocity. Now the next part we need to do is we need to solve for our braking impulse. So the reason I put a square bracket around this is because this is the braking impulse. And so like I noted earlier, impulse is this. Well, Rx is just a type of force, so we could say impulse is equal to Rx times time. And since we have Rx times time already solved for, we know that our impulse is just going to be equal to negative 108 times our time, which is 0.2, which we already solved for and know is negative 21.6. All right, guys, so that wraps up the impulse and momentum lab, and I'll see you next week.